Okay, my name is Trey Moberly. I am currently living in Leroy, Illinois, which is a small town in central Illinois between Champaign and Bloomington. I currently work in Champaign at an outpatient orthopedic clinic. We also do a lot of sports medicine there, so I've worked with a lot of athletes in my past. I've worked at that clinic for about 6 years, and a couple fun pieces of information about me. I have a son who's 8 years old, keeps me busy. He's in the middle of baseball season right now. And then we also have a Persian cat named Amigo, who is entertaining to say the least. Today we're going to be talking about different types of force, starting with the use of a slinky to show compression, tension, shear, and torsion. Got a Mickey Mouse slinky here. So to discuss compression, which is going to shorten and widen the tissue, this is going to be equal and opposite loads applied in an inward motion. The opposite would be tension pulling outward with equal and opposite loads, and that's going to cause that tissue to lengthen and thin. As you can see, the slinky thinning here as I pull out, and then it will wide and compress or shorten with that compression. The next movement or motion will be shearing here. Easier to show in a vertical pattern. Shearing is going to be an internal kind of angular deformation here that also lengthens these inner tissues. You can see I am providing a pressure, a force kind of parallel to that surface of the structure, and it's going to be opposing loads, one coming or just opposite directions there. So we're going to kind of combine those two different loads to create torsion, which is going to be again that shearing in a parallel and perpendicular manner, and then the combination of some of the compression and tension to create the torsion here, which is going to be the shear and then that diagonal stressors to create that torsion. Pretty flexible slinky. Most things you'll be able to really see that restrictive, but this really shows how you can get that rotational aspect to it if you can see the patterning on the slinky twisting as I apply that force there. Okay, moving on to different types of bending. We're going to start with 3-point bending, utilizing my ruler here and a pencil sharpener to apply 1 point in the middle. I'll use my fingers to apply 2 points on the outside, and you can see as I apply these equal forces here, it causes that ruler to bend. If I were to meet the yield point, it would snap in the middle over this 3rd point there. So that's 3-point bending. 4-point is going to be similar, but instead of having 1 point in the middle, I will have 2 points on the outside with my fingers still, and then 2 points just inside of those, which creates some force coupling. Same sort of bend here as I apply those forces together. It's going to be 2 equal moments that would also create a fracture or the snapping of that ruler if I wanted to break my ruler today, but I don't. So something I will be comfortable breaking is a rubber band. We're going to use this to answer the 4th question, talking about what happens to tissue in fatigue failure. So as I apply a force on this rubber band, if I get past that yield point, the tissue can reach the plastic range and would be unable to return to its original state. In the terms of the fatigue failure, if that strong load over time causes the fatigue when repeated, the tissue can rupture due to that overexertion of pressure past what the tissue can hold. So once it hits that breaking point, the quicker the load is applied, the easier it is to break, but you can reach that force with, while easing into it or with a quick load. So the more strain and stress, it'll cause that to snap, and that's what can happen to your tissue if it reaches fatigue failure. Thank you.